All right, let's talk about hearing. Thank you. Some of you actually get it. So what we got to do is, why are we talking about hearing? I know it's tempting to jump into and just randomly copy down vocabulary words and memorize definitions, but it's missing the big point. It's missing the big point. The big point is, what's called transduction. How does environmental energy, which is basically kinetic energy of moving air molecules, how does that translate into a joke? How does that translate into sarcasm? How does that translate into your favorite song that you wear out by just hitting repeat and repeat and repeat? And again, we don't want to lose track of, for lack of a better word, the majesty of mind, body. So your body is basically inside your ear. We're going to talk about this. Inside your ear, you got a couple things that vibrate. How do these things, these bones, and then a bony thing filled with fluid, when that thing vibrates and has different waves shudder through it, how does that translate into someone saying, hey, someone saying, you're ugly? Some kid's like, yeah, I know. How does that actually translate into meaning, into thought? That's the miracle of transduction. So we're going to kind of take it apart down to the very bottom. We're going to talk about sound, and then we're going to talk about different structures and functions of your ear. All right, so let's jump into this. We're going to talk about what is sound. What is sound? Just like we talked about what is vision, well, if we're going to talk about what is vision, we had to talk about what is light, what makes up light. And so now we're going to talk about, when we talk about hearing, we have to figure out what exactly are we hearing? What is sound? Sound roughly has 3 parts. The easiest description is sound is just vibrating air molecules. And we can detect a pretty wide range. And we talked about this when we talked about just noticeable difference. And we talked about the ability and how sensitive we are to pitch changes. What does that mean? We can detect sounds from as low as what's called 30 hertz, which is cycles per second. That's pretty low. That's like a whale burp. Imagine something really big. Imagine how deep and low pitch a whale burp would be. Would anyone here like to imitate that or estimate that, please? Not bad. I'm impressed. That was a good one. 20 hertz would be like a mosquito shrieking at you in frustration. It would be so high pitch to be almost imperceptibly shriek-like trilling. We can really detect a wide variety here. So we're sensitive to pitch. We're sensitive to different sounds there. When we look at pitch, we have pitch equals frequency, frequency equals pitch. So let's make kind of a mental chart if we can. Frequency refers to stimulus, that's the energy. Pitch is the sound. Frequency happens outside of the body. Pitch happens inside the body. Frequency happens outside the body. Pitch happens inside the body. Pitch is, again, you know what? Let's do this. I gotta first start with the ladies, because generally ladies are more courageous and more willing to kind of flirt with the line between what is masculine and feminine. So who is the shyest girl in this class? Good job. She's like, what'd I do? Can you, in the deepest voice you got, can you say Megatron must be stopped? As if Optimus Prime himself was saying that. Got to go deep.
Megatron himself must be stopped.
Not too bad. Try it. No? Why so shy? Look around this class. Is there anyone here whose opinion matters to you? All right, so maybe the lady. I'm surprised. I thought the ladies would be a little bit more adventurous. Maybe I'm wrong. Let's try this. All right, fellas. Now it's your turn to step up to the plate. Oh, proceed, ma'am.
What did you say about frequency outside the body and what?
Frequency is outside the body. Pitch is inside the body. Where's one of the fellows who's afraid? Here's all I need you to do. I need a fellow to volunteer.
Why don't I get that at all?
All right. Michael. Really? You don't even know what it is. You just don't want any part of it.
See what it is.
Say, I'm a little teapot in a high-pitched voice. Is there any guy who's going to try it in here at all? Why aren't you doing it?
My voice is already high enough as it is.
Wow, so it's like that. All right, proceed. How many of you all feel uncomfortable now? And we're going to talk about this in another unit. We talk about human development and why when you get to adolescence, gender behavior becomes extremely exaggerated. Adolescent males become obsessed with physical power and what car is faster, who's got more horsepower, who can bench what, and ladies can't go anywhere without makeup. What up?
Can you say it? Yeah, you do.
Okay?
Can you say it?
Nah, I can't. A long time ago, my voice coach said I shouldn't straight yet. All right. When we say we're going to make a chart, we got the concept. Okay. What's that? I told you, my voice coach said I should not strain my voice. All right, so check it out. We got body. We got mind. Body is going to refer to receiving what's called outside stimulus. All right, and then mind is going to be inside perception. So when I say outside of your body, you're going to have what's called frequency of waves. Frequency of the waves, the vibrations, the air molecules hitting your eardrum. And your mind, you're going to perceive that as pitch, whether someone's off key or not off, someone's on key or off key. All right, and I'm going to need a volunteer next week. What I'm going to need is someone who's really courageous to be able to maintain a note, okay, for a couple seconds as you walk towards a brick wall. And here's the theory. If you have your eyes closed, your dominant sense, you won't be able to tell how far away you are. But if you can maintain a perfect note, so the only thing that's changing is not the pitch of your voice, but how close you are getting to the wall, that sound will bounce off the hard surface of the wall and hit your ear, and that sound will change. And as a result, you'll be able to tell how close to the wall you're getting. And I'm willing to bet if we have a courageous volunteer, they'll be able to get within 1 inch, their nose 1 inch of the wall, really close, just by using the echolocation concept of something bouncing off a wall and coming back. All right, so on your mark and set, let's jump on to sensation lecture notes. Here we go. Loudness. All right, is amplitude. Loudness inside your ear, inside your mind. Amplitude outside. Why is this? Because loudness is an opinion. Have you ever heard your parents say to any of your songs, hey, can you turn that up? No. See, the volume is neutral. I'm sorry, the amplitude is neutral. The amplitude is neutral. It's energy in the room. But opinion as to whether it's too loud or not loud enough, that's perception. That's inside the mind. So we want to make a distinction between external stimulus and internal perception. This word right here, timbre, it's spelled with an I, but it's pronounced timbre. Now this is what's going to be called the shape of the sound wave. The shape of the sound wave. We've talked about sound. Let's talk about parts of the ear. This, just as we went through relatively quickly with parts of the eye, we don't need to make this any more difficult. We're going to try to reduce these complex definitions into 1 or 2 word metaphors. All right, so parts of the ear. Skip the ear. So you need to copy down the ear. Okay then. The ear. So now that we've got the ear copied down as your subtitle in your notes, let's write down the first part of the ear we're going to talk about. We're going outside to in. It's going to be called the pinna. Do you just like to say things like that? All right then. So here's what I want you to do. All you got to write down is the part of the ear that nerves get flicked. If you're a nerd, you know what I'm talking about. And for this class only, if you're sitting beside someone, if you're sitting behind someone, you are allowed to flick their ear randomly throughout the class. All right? So just randomly flick someone's ear. So the pinna is what nerves get flicked. Got it? It's the only thing that you should get pierced. Your ear better stop hitting her finger. Tympanic membrane. Tympanic membrane is a fancy name for your eardrum. And let's look at what a drum is. A drum is basically a cylinder with something tight stretched across it. And so basically that's what your eardrum is. What is the cylinder? It's your ear canal. What is your ear canal? It's the place where you put Q-tips. Notice that nobody cleans your ear with your thumb. And if you do, that's not smart. And I don't understand why people would even try that. Some of you don't believe me. All right, let's do it. Try it.
It doesn't fit.
How do you know? All right then. She said, ow. All right, so let's do this. Let's talk about your ossicles. Ossicles are 3 fancy bones. Ossicles are a fancy name for the 3 bones inside your ear. Yes, you do have bones in your ear. And so let's talk about what these are. 3 small bones, and the easy way to remember them is a hammer, anvil, and stirrup. And they bang against each other. That's what a hammer does. That's what an anvil does. Hammer bangs against an anvil. And when you think about something banging against something other, we're creating vibrations. This whole process is what I would call a Rube Goldberg process. I suppose Mother Nature or God had a great idea for making the process of auditory transduction really complicated. Hold on for a sec. I want you to imagine the game Mousetrap. Are you know what I'm talking about? The game Mousetrap where you had to build a thing and the thing falls down? It's like the most complicated way in the world. Did anyone actually play the game or did you just have fun building it? Yeah, you did play it? Yeah. Okay, I don't judge. I just short-circuited through that. All right. So what are we talking about? This whole process is your pinna is kind of like a satellite dish. It's shaped to point sound, to bounce sound vibration into your ear canal. And your ear canal, the place where you put your thumb, all right, the place where you put your thumb, ow, that's going to be like a big cave. And if you ever shout in a cave, the sound wave is going to echo across the cave walls. And then it's going to hit your eardrum, and your eardrum is going to vibrate. And then your eardrum is going to vibrate the hammer. And what is the hammer going to do? It's going to hit the anvil. And the anvil is going to vibrate. And that's going to make your other bone called your stirrup. And that's going to vibrate. The whole process is like the most convoluted thing. And then we haven't even talked about the little curly Q snail shell thing filled with fluid that once that hits, waves go in the fluid. I don't know who did it. It seems like there's too many steps, but that's not my place to say. So let's keep going in our process right now. How many of y'all wish you had more vocabulary words to write down and know? Good job. So here we go. Your hammer, the vocabulary word you know is called your malleus. M-A-L-L-E-U-S. Your hammer is also known as your malleus. And if you're having trouble figuring that out, think of a mallet. Hammer and mallet. Malleus. That's actually where it comes from, the word mallet. Has anyone ever played a game of croquet? Have you ever finished, or do you just end up hitting the ball all over the place? Yeah. No one ever finishes a game of croquet. It's crazy talk. It's much more fun to randomly swing a freaking mallet near your brother or sister's head. All right, so we got malleus. Your anvil is going to be known as your incus. And your stirrup is going to be known as your stapes. Go ahead.
Wait, so when you get your ears pierced, are you breaking a bone?
No, goodness, no. All right, your bones that we're talking about are inside your skull. Right, they're legitimate bones. When you're getting your ear pierced, unless you do it wrong, it should only be on the pinna. All right, if you're like have someone pierce inside your ear, number 1, ow. All right, number 2, make sure they wash their instruments because there's going to be an infection. And number 3, ow. Okay, let's talk about your oval window. Your oval window is where the stapes hits. The oval window is where the stapes hits the snail shell. You're like, what? What snail shell? Well, I'm going to tell you that in a second. But for right now, just write where your stapes hits the snail shell. Because remember, vibrating air molecules get collected by your pinna, pointed to your ear canal. It bounces inside your ear canal, hits your eardrum. Your eardrum is attached to what's called your malleus, which is your hammer, and that's going to hit the anvil, and that's going to send a vibration to your stapes. And your stapes is going to hit this thing called a little curly Q snail shell filled with fluid. And if you know what that is, I double dog dare you next time you have a glass of water. Just flick it a little bit. And if you have a container filled with fluid, and you flick it or touch it, you're going to see little vibrations or ripples in the fluid. So we've continued the vibrations. First it was air vibrations, and then it was vibrations of a solid hitting another solid. Then we're going to have vibrations, fluid vibrations. Now let's talk about your cochlea. Now, the word is cochlea, but I suggest, and I'm willing to make a bet with you, and I will pay you with a sticker if you can do this next task and not be a little bit happier. The word is cochlea, but I'd like you to say it in a British accent and see if you're not a little bit more happy.
Cochlea.
Are you kind of happier? You kind of are. Cochlea. All right, it's just much more cheerful. It's shaped like a snail shell. Why is that important? Meh. Why did we have to know the hippocampus is shaped like a seahorse? Why do we have to know the amygdala is shaped like an almond? So we know the shape of it. Where is the location? Well, if you put your thumb in your ear and push real hard, you'll find it. What is the function of it? So we know the area, we know the shape. What's the function? It transmits vibrations in fluid into electrical energy. That's the point of it. It takes vibrations in fluid into electrical energy. So first there's vibrations in air. Then there's vibrations in solid as your bones bang against each other. And there's going to be vibrations in fluid. Now when we talk about fluid vibrations, maybe back in the day you were young enough that you went to like the local pond and you threw rocks in the pond because you really had nothing better to do. When you're a little kid, that's endlessly fascinating. So you throw a rock in a pond. You throw a rock 10 feet away and it makes a big splash and it makes ripples. Now I want you to imagine those ripples coming back and they're going to reach, for lack of a better word, where the beach, where the water meets the land. Right around there you're going to have little plants, pond grass or seaweed or whatever it is going to be. As the waves crash upon the beach, they're going to wave those little seaweeds or grasses back and forth. Let's use that metaphor for talking about what happens inside the cochlea. And the idea is you have little hair cells in there. And as the fluid is vibrate, you're going to have a wave traveling through this snail shell-like thing. And the snail shell-like thing has little grasses in it, or hair cells. When the wave crashes or stimulates the hair cell, that's how we hear, because that hair cell is attached to a nerve. Now, where in the cochlea that hair is stimulated determines the type of signal. Wait a minute, I want to say this again. Now follow me along with this. The space, you know what I'm saying when I say the word space, the space inside the snail shell-like cochlea, where the wave crashes determines the type of signal. Y'all smell that? That smells like spatial coding. So let's try this again. Write this down. The space inside the cochlea where the fluid hits, the space inside the cochlea where the fluid hits determines the type of sound. If the wave hits close to the oval window, what are we going to say? We're going to hear high-pitched sounds. So let's take a look at this. If you have your pinna, it's going to collect sound, kind of like a satellite dish or orchestral band shell. Vibrating air molecules are going to bounce off this cave we call the ear canal. It's going to hit your eardrum and vibrate. You got your hammer, which quite frankly looks like a chicken drumstick. And then it's going to hit your anvil, because that's what hammers do. Then it's going to hit this thing, oh my gosh, that looks like a horse's stirrup. Which, by the way, if you ever take world history, you ever study military history, is probably the most amazing military invention in the history of anything. A stirrup on a horse's saddle. This allows people to stand up in a saddle and fight from a horseback. Pretty cool. But I digress. So, kind of random little history fact. So we got this idea called a stirrup, and it's going to hit on this window that's shaped like an oval. What do you think it's called? The oval window. This oval window is going to bang inside the cochlea. The cochlea is going to set little vibrating fluid going around and around and around. Where the vibration crashes upon the shores inside the cochlea is going to determine what type of signal. If it crashes close to the oval window, it's going to be a high-pitched sound. Gentlemen, demonstrate a high-pitched sound. Not bad. If the wave crashes towards the end of the snail shell, it's going to be a low-pitched sound. Ladies, give me something low. Not bad. Not bad at all. So that's spatial coding. Now let's talk about temporal coding. What if that wave hit that place a lot? What if that wave hit that exact same place a lot? What if that wave hit that exact same place a lot? I know I'm repeating things because I'm talking about the rate of firing per second. That's temporal coding. The rate of firing per second. So if that wave hit that exact hair cell in a certain space a lot, that's going to be loudness. It's going to be the intensity of the sound. Temporal coding is going to be intensity. Spatial coding is going to be the type of signal. Questions on auditory transduction so far? Proceed, sir. How fast is that whole auditory transduction system? Well, think about it. What if it is slow? What if by the time I say a word, hold on for a second, by the time I say a word, leaves my voice box, vibrates across, and hits your ear, If it's really slow, let's say it takes 5 seconds. That means you're actually in the past, because what I said, you're processing 5 seconds after I said it, and I'm actually already over here. That would be freaky. So it's got to be pretty fast for you to be in the present, because if it was really slow, you're processing things I said 5 minutes ago. All right, question.
So last year, someone was playing through a really high-pitched noise, and all the students could hear it, but the teacher couldn't hear it. Why is that?
So here's the way that works. With older folks not being able to hear a higher pitch, what that generally means is throughout their life, the first part of the cochlea that's hit is the higher pitch frequencies. And if that is hit throughout their life for 10 years, 20 years, 30 years, 40 years, 50 years, especially people who've listened to loud music and or artillery officers in the military, that ability to hear high-pitched sounds, those hair cells, imagine if you walk on grass over and over and over. The grass is sticking up, gets tramped down, gets tramped down, gets tramped down, and eventually dies. That's what happened to those hair cells. And it's kind of frequency specific is deafness. Go ahead.
Do sounds cause headaches?
It could be. Well, we'd have to define what is a headache. All right, so, why would you ask a question when you know I'm going to dodge it? See these 3 semicircular things that hold fluid? Well, if you think a thing that holds fluid is called a canal, and you have these 3 things that are semicircular in shape, you know what we're going to call them? The 3 semicircular canals. All right? And this is how we know balance. It's hard for you to understand this, so here's what I want you to do. I would like you to go read a book on the long family car ride vacation. In the back seat, in the middle seat. No one likes that seat. All right? Everyone's starting, I can see the disgust. How many of you all get car sick when you read in the car? And the reason is because your brain's dealing with 2 signals. When you're sitting in the back of the minivan and you're trying to read and ignore the family nonsense around you and the Cheerios funk from your brother and sister in their car seat and the sippy cup, and I got bad memory. So what am I saying? You're reading your book and you're trying to zone out the world, and your eyes and your book are not moving. Well, relative to the car, because when the car goes up, your eyes go up and the book goes up, and that's fine. But the reality is your body is moving in proportion to the environment and gravity. Every time the brakes are hit, you go around a curve, the acceleration's hit, or you hit a bump, your body is moving. The fluid in your 3 semicircular canals are sloshing around. It's telling your brain, hey, you're moving. But your eyes are telling your brain, no, you're not. Your brain's like, what the F? Stop this. And so what your brain's going to do is your brain's going to get car sick. And your brain's going to say, put the book down. All right, so here we go. Questions on your 3 semicircular canals and balance. Let's take a look at drawing that stuff out, your 3 semicircular canals. We're going to basically go here. So if we have kind of like a little horseshoe thing, let's imagine we're going to have a fluid level in here. And on the inside of these things, you're going to have little cilia, or otherwise known as hair cells. When you move your head, and blondes know what I'm talking about. Oh my God. All right, so blondes, if you understood that, you'd be mad, but she's like, that's okay. All right, so, oh, you feel bad for her? All right, never mind. I'll tell you, I don't judge people to their faces. All right, but behind their back, yeah, I judge. So check this out. If you were going to then tilt this thing, notice that the water level, the fluid level, is going to maintain the same, a constant with the horizon. So what does this mean? This clearly means that different cilia are going to be hit. And we know the cilia that are going to get sloshed around by the fluid in there are connected to nerve cells. These nerve cells are bundled together. Now, just as your eyes send signals to your occipital lobe, what part of your brain controls balance? Hangs off the back, looks like a butt. Cerebellum. So your cerebellum is going to receive the balance signals, but your 3 semicircular canals, collectively known as your vestibular system, are going to send the signals. So check it out. We got hearing, we got vision, we got taste, we got smell, we got touch, 5 senses. Or do we really have 6? Because we have the sense of balance. Or are there more senses as we kind of go through our lesson? We're going to kind of do this, and maybe, we'll take a look at, is there such a thing as ESP? I know everyone wants it to be true, but we're skeptical. How many of y'all want there to be ESP? How many of y'all are afraid to admit that you really believe it? Or you're like, I don't believe, that's stupid, that's dumb. All right, let's go back to this. Your basilar membrane is a thin membrane inside the snail shell that has hairs rooted in it. And the next word you're going to have to know is called your organ of Corti. Your organ of Corti is, for lack of a better word, the metaphor is your ear's microphone. That's where the actual magic happens, where vibrations are turned into electrical energy. Vibrations are turned into electrical energy. That's the point at which you say transduction happens. Whenever I've taught this class, or sensation with eyes, or sensation with the ears, or anything, a lot of times students are going to ask, well, what happens with the extremes? When we talk about vision, people say, what happens with blindness? When we talk about hearing, what happens with deafness? And I think that's important because we want to look at the extreme examples, because the extreme examples let us know what's happening in our brain. So let's look at the extreme of hearing. And one extreme, I mean, if we do a bell curve, or also called a Gaussian curve, most of us are near the middle. We got some people who hear really well. They're super hearers. And some people are deaf. If we study the super hearers, it's going to give us an indication of what happens in normal people. And if we study people who are deaf, it's going to give us an indication of what happens in normal people. So we study the extreme. So let's study deafness. Deafness is a symptom. Just like I think depression is a symptom. It's not enough to say someone's deaf. That's a label. That's a meaningless word. It's not enough to say someone's depressed. I want to know why. What type of depression? Give me more data. And so when we find that deafness is a symptom, we're going to have two types. One of them is going to be conduction deafness. And conduction deafness is physical. The vibrations aren't going anywhere. And there could be a lot of reasons for that. Conduction deafness itself is a label. It's a category. It's not enough. Maybe you have too much earwax. Kind of nasty. Old people specifically have that. Maybe you have an infection. So the tissue inside your ear is swollen shut. As a result, vibrations don't go anywhere. Maybe, as you said, the bones inside your ossicles you're broken. Maybe your eardrum is ruptured. So conduction deafness is a physical problem. Vibrations are stopped. The next one is going to be nerve deafness or neurological deafness. That's the tougher one to fix because we know neurons and nerves, it's a pretty tough thing. You can't go in and surgically fix someone's neuron. It's much easier to irrigate someone's ear canal and have a whole bunch of nasty yellow wax come on out than it is to do neurological treatments. And then Monday, we're going to have our psychology party. Yes. I'm going to bring Hershey Kisses and lemon.
In a lemon?
Yeah, we're all going to take turns licking it. Can we get this thing over with so we can minimize our time together? I'm not afraid to go back to jail.